this video, we will learn how we can use Creo Mechanism to actuate different movable assemblies. So this is an assembly that we've made in a previous session where we have two gears mounted on pin joints and a gear connection between the two spur gears. So when we move the first gear, the second gear moves as it should based on the mechanics of the gear train, and over here we have a slider connection where this piston can reciprocate up and down within prescribed bounds. One way of actuating it, just to verify whether things are moving the way they should, is using the drag component or control and alt as I was doing right now. But if we want to carry out methodical analyses where we want to move the parts in a certain prescribed manner and then observe the movement of the overall mechanism or particular points in the mechanism, then for that we need to be able to actuate it in a prescribed manner, and for that we in Creo will use what are known as servo motors. There are different kinds of analyses that we can perform in Creo. We right now will be looking at kinematic analysis, and kinematics, you know from your courses in physics and mechanics, is the kind of analysis where we don't worry about the forces which are acting on our system. We don't worry about F is equal to ma. We don't need to prescribe the mass of our system. We tell the system that we want you to move from point A to point B along this trajectory, or we want you to spin at this particular angular velocity. So we tell it details about the motion that we want it to perform. And then in response to that motion, we can look at different aspects that we are interested in. We'll go to application and we'll select mechanism. Now we are in the mechanism tool in Creo. And what I want to do is that instead of rotating this gear manually, I want to rotate it at a particular RPM, at a particular angular velocity using a servo motor. So take a quick minute to look at the model tree, which now we have two model trees, two portions of the model tree. We have the top portion, which is the assembly model tree that we've been working with. We have the gears assembly and the different part files that are a part of that assembly. Below that, we have a second model tree, which is the mechanism model tree. And in this model tree and in this tab, we'll provide details of different motion analyses that we want to perform, and then look at the results and analyze the results. Similar to how there are different components of a geometric model tree, there are different components of a motion analysis model tree. The first one that we look at are motors. Motors, as the word suggests, are tools that we can use to actuate different components. We learn how to prescribe motors. Right now, there are no motors prescribed. In Creo, there are two different types of motors. We are looking at servo motors right now. There are different movable joints which can be prescribed in Creo, as we've learned, and in the mechanism model tree, we can see that there are three movable connections that exist over here. If we go through these, Creo will tell us which connections are we referring to. So this connection is the one in the back, which is the slider connection, and then these two connections are for the two spur gears. And these are listed over here because these are movable connections that can be used in mechanism analysis. Other tools that we'll be using over here are analysis and playback. So we'll get to that later. The first thing that we want to do is to tell Creo that we want this gear to be rotated at a certain speed. And we can prescribe servo motors from here or select servo motors from here and then select the driven entity. For us, the driven entity is this gear, and the motion would be about its pin connection. So we'll select the pin connection from here using this icon for a revolute joint or a pin joint. Now we have selected our driven entity by selecting the motion axis, and then we'll tell Creo how do we want it to move. We want the profile, the motion profile that we are prescribing, we want that to be in terms of angular position, angular velocity, angular acceleration, or torque. Creo knows that the kind of joint that we selected, that's a rotary joint, it's a pin joint, so it's giving us angular motion prescription options. I'll select angular velocity, and the units of angular velocity are degrees per second, and I'll tell it what kind of a function do I want my angular velocity profile to have. In your notes, I have copied this table from Creo's manual about the different kinds of functions which exist in Creo and that can be used to prescribe different motion details. So the constant function, that's the standard function where you give it a number and that number is your input. You can also use ramp functions where your value increases from a small value, normally 0, to a higher value, and that is of this form. There are different other functions as well. We'll look at those later. But for now, let's select the function time as constant. So in this context, what we mean is that we want this pin joint, this component which is pin jointed, to rotate at a constant angular velocity, which we will prescribe in the units of degrees per second. If we had selected angular position, then constant doesn't really make sense. But let's say that it did, then whatever number that we defined, that would have been in degrees. One of these other functions would have made more sense, that we want the angular position to increase from 0 degrees to 20 degrees over a ramp, or we wanted to perform a sinusoidal behavior, and we can prescribe the details of that sinusoidal behavior through the cosine function. But for now, we are prescribing angular velocity, constant angular velocity. After selecting that, we'll go to profile details, and over here we'll select the value of our function. Remember, for a constant, a is the constant, so the output would be the number that we enter over here. So let's say that I want my gear to, if I want my gear to complete 1 revolution every second, then it has to perform 360. It has to sweep 360 degrees per second. But let's say that I want it to complete 1 revolution in 3 seconds. So I'll divide this by 3, and I'll ask my gear to rotate at 120 degrees per second. So what I've done now is that I've added a servo motor. So now if you go to this model tree and look at servo, there is a servo motor that you've defined. You can modify its details as we do for other functions in Creo, but just to verify, we have constant angular velocity of 120 degrees per second prescribed. Now we have a motor in our arsenal. You can think of this as having connected a servo motor that spins at 120 degrees per second to this gear. To carry out a particular analysis, we need to tell Creo that I want you to run this motor for this many seconds, and then I want you to measure the following parameters. So that's what we'll do next. And that we'll do from the analysis tab. You can select analysis from here. You'll select an analysis from here, mechanism analysis, and you will define a new analysis. Give this analysis any name you want. I'll call it my analysis, and There are different types of analysis in Creo. What we are focused on right now is kinematic analysis, where we prescribe details of the motion. Later on, we'll learn dynamic and static analysis as well. Dynamic and static analysis involves the use of forces, so we'll have to prescribe frictional forces, gravitational acceleration, and the mass of the body for it to be able to calculate the force acting or the acceleration on that body. But what we are doing right now is kinematic analysis. We want our analysis to start at time 0. We want it to run for 10 seconds. Let's reduce that to 6 seconds. And we want it to have a frame rate of 10 frames per second. So we wanted to perform one calculation every, we wanted to perform 10 calculations every second. Let's increase this to 50 frames per second. This will increase the computational time. And let's keep the initial configuration at current for now. I'll explain what this does later. So these are initial settings for our mechanism analysis. Next, our mechanism analysis is only useful if something is moving. So we'll tell our mechanism that we want it to move by the action of the following motors. Right now, it's already added a motor. Let's remove everything. So in this tab, we add motors, and these are motors that we must have previously defined. And I'll add a new motor over here by selecting this option. And if we had multiple motors, Creo would have given us the option, but right now we only have one motor. This is the servo motor that we defined over here. And I'll ask it to use this. I'll ask it to start running the motor from 2 seconds and run it till the end. So you can have a motor in an analysis, and you could enable it to be active for a particular duration. We can add another motor. Let's say that if you had a second motor which rotated in the opposite direction, and we wanted it to act after the first motor ended its action, then we could add it over here. What we'll do now is that we'll ask the first motor to run from 1 second to 3 seconds, and the second motor, which is in this case the first motor acting for a second time, to run from 4 seconds to the end. So there should be a pause between 3 and 4 seconds. Let's see if that happens or not. So this is how we've defined an analysis, and then when we click run, it should perform that analysis. So I hope you were able to see what has happened. I'll run it again, but instead of running it again, I'll show you a different way where you can run it. So now if you go to analysis, that analysis did not show up. Let me quickly define that analysis again. So now if you look at your analysis option over here, it has a drop down menu, and this analysis that you defined, which I did not remember to rename for the second time, it has its default name that shows up over here. You can run it from here by clicking the run button. When you run it, it initially runs for 4 seconds, pauses for a second, and then runs for another second. Let's say that we wanted to do this, but then reverse direction at the end. So what we can do is that we can define another motor. Sorry, my program crashed, so I had to quickly restart. So we have one functioning motor, and we have an analysis set up. When we run that, things move. Now we want to add a second motor with different details, and we'll use a different method this time around to add a motor. So you could have done the same thing, go to servo motors, then select the axis about which you want to apply that servo motor, or you can go to connections over here, and as we saw, all the movable joints that you have, they are listed over here. Right now you have 3 movable joints. You have joint 1, which is this pin joint, which is highlighted green, this slider joint, which is highlighted green now, and this pin joint, which is highlighted over here. And pin joint is a rotational point. So if you open this joint in the drop down menu, you have a rotational axis. and you can select this rotational axis, left click it, and it automatically gives you the option of applying different actuators to it. The actuator that we are working with today are servo motors, so we can apply a servo motor from here, and that would directly apply to this movable joint, and it's a rotary joint, so the motor would be one that rotates our part. The profile details that we'll prescribe now would have the opposite direction, and let's make it faster. Previously we had 120 degrees per second. This time around let's give it 150 degrees per second. And remember that we want to work with angular velocity, so for it to be degrees per second, select angular velocity from here, it's minus 150. Select OK, and in our analysis that we had previously set up, it's running for 6 seconds. Add a second motor, and when you add a motor now, it gives you two options because we have two motors available. Add the second motor, we'll let the first motor run up to 2 seconds, and then from 3 seconds to the end, we'll let the second motor run. So what should happen is that the gear train should move in one direction, pause, and then move in the opposite direction. Let's see if that happens. That's what it does. To make it more obvious, let's increase the duration of the pause. So in this way, you can add multiple motors, and each motor could have its own motion details. This is the simplest way of just telling it a constant RPM, but you could give it an RPM that ramps up or that's sinusoidal, and you know how you can do that by going to your motors and choosing appropriate functions. So once we've carried out this analysis, the results of that analysis exist over here. And let's see how we can look at those results. If we want to play what just happened back, there is a playback feature, a new playback file that is created, and that is referring to the analysis that we just performed. So then the name of our analysis is analysis definition 1, and the name of the playback file is the same. If we click this, this command opens up where we can manually go frame by frame. We are running at 50 frames per second for 6 seconds, so a total of 300 frames. Or you could click play and it takes you to those frames. This is not real life, so this is not real time, so this is not actually spinning at 120 degrees per second. For your convenience, you can increase or decrease this playback speed. And if you want to save this video, you can select capture. Before I do that, by the way, because I have this loop option enabled, the playback will continue running until I tell it to stop. So this time around, after it's finished running, it won't restart. If I click capture, I can save this video, I can record this video as an AVI or an MPEG, give it a name, adjust the resolution, and select the same frame rate as you had selected in your settings if you want the video recording to play in real time. If I select 50 frames per second over here and the analysis was done at 50 frames per second, then the video that will be recorded will show me two gears actually moving at 120 degrees per second. This is how you can save videos. And when we perform analysis, we also want to measure different things. So as a part of one of your assignments, your projects where you need to make a gear train, you need to report what is the angular velocity of the inlet gear, the input gear, and the angular velocity of the output gear, and also the angular velocity of some intermediate gears if you have a long gear train. So for that, we have to define a new measure. So if you go to analysis, there is this command over here, measures. And measures you can think of as virtual sensors. So we will place a virtual, in this particular case, velocity sensor, and we can place it anywhere. So create a new measure, and I want to position it on this edge. I'll select this point on this edge, and what I want to measure right now could be position, could be velocity. For now, let's measure the velocity. It will measure the linear velocity. It doesn't measure the angular velocity. It will measure the linear velocity in inches per second. You can tell it to measure the x component, y component, or the z component of linear velocity or the magnitude. I'm interested in the magnitude. And once I have defined that, I can rename it the name of the parameter. I'll call it gear 1 velocity. Click OK. I'll define another measure, which will be the same thing for gear 2 velocity. I'll measure it at this point. You can measure it wherever. You can measure it over here. Let's measure it over here. And click OK. Now let's ask Creo that for the analysis that we just ran, tell me how the velocity changed with respect to time. For that, first thing we have to confirm is that we are making a graph which is a function of the measure. The measures are the instruments, the sensors that we just defined versus time. You could have measure versus measure. For example, you might want to plot the velocity of gear 1 versus the velocity of gear 2, x, y. So you might need to do that, and this is where you can choose those commands from. So what I want to do is that I want to make one graph versus time of both of these measures, the velocity of gear 1 and velocity of gear 2. And this is the button where you can tell Creo to make you a graph. Right now it's grayed out because Creo isn't sure which analysis are you talking about. Give me data, Creo is saying, and then I'll make a plot for these parameters. And to give it data, you have to select a result set. And corresponding to each analysis, there is a result set which is generated. And for the analysis that we performed, this result set has been generated. If you double click it, that result set is loaded. It was not computed because the analysis that we carried out was a position analysis. And in position analysis, it doesn't compute the velocity. So make sure that we are working in kinematic analysis. I went back, fixed that to kinematic. I'll run the analysis again. And now when I go to measures and run this analysis, load the data from that analysis, these parameters now have data, and we can plot them using this command. Because we selected linear velocity, which is the vector sum of all three components, and our angular velocity is constant, then our linear velocity stayed constant. And since both the gears are moving at the same speed, because they have a gear ratio of 1, the angular velocities for both should be the same. But the linear velocities are different because we selected two different points. If we 2 points at different radial distances. In your analysis, you have to report the angular velocity. So for that, you can measure the radial distance from the center of the gear to the point where you were measuring, and use that with the linear velocity to calculate the angular velocity. You can export data from your results using this command, which exports data to an Excel file. You can give it a name, and from that you can post-process that data. Let's rerun the analysis, because this time around it did not engage the second motor. So I'll modify our analysis to have the second motor run from 4 seconds to the end. And let's see what effect that has on our results. Go to measures again. Load the results from the latest analysis, and then plot them over here. And you see now things do change. Initially, things were running at one linear velocity, then they dropped to 0 because your gear was not moving. And upon resuming its motion, they did not go to an initial value because initially things were moving at 120 degrees per second and then they were moving at 150 degrees per second. Even though they were moving in the opposite direction, this is the magnitude of the linear velocity. That's not reflected over here. But if you look at the components, you can discern that as well. Let's modify our point on gear 2. Instead of it being closer to the center, let's have it at the very circumference. And now when we rerun the analysis, these two should be identical, and that's what's happening now. So in this way, you can run your analysis, generate playback videos, and look at different motion results, plot those results, export those results. One thing that I haven't talked about, but I'll invite you to work on your own, is how you can modify the labels over here. So over here, measure isn't really that useful. What you should present is this saying velocity magnitude with the units in parentheses. The units are inches per second. So that's how you can prescribe a rotary servo motor. Very quickly, I'll talk about how you can prescribe reciprocating a linear servo motor as well. So similar to how we prescribed the motor for the second time, we'll find the connection, the movable connection that we want to talk about, that we want to reference. In this case, it's this connection, this sliding connection, and it's actually a cylindrical joint. So it has one rotational degree of freedom and one translational degree of freedom. We are interested in translating it. Select translational axis and add a servo motor. This time around, Creo knows that this motion that is about to be prescribed will be translational. So over here, it's telling us that this is translational motion. Previously, it was telling us it was rotational motion. And we can prescribe the profile details. I'm just opening them over here because I ran it previously from here. I will prescribe velocity. This time around, it's linear velocity. And I will use a sinusoidal, a cosine function. You can refer to this file over here to see what different parameters you're talking about. A is the amplitude of your sinusoidal function. T is the time period. I'll give it an amplitude of 0.5 inches per second and a time period of 3.5 seconds. So it repeats a period every 3.5 seconds. So this is a sinusoidal profile of linear velocity that I am going to ask Creo to actuate my reciprocating joint according to. So I prescribed a new motor. If you go to motors now, you'll see a new motor has been defined. Motor 3, horrible naming practice on my part. I should have been more clear about that. I'll define a new analysis now. I'll run the analysis for 5 seconds at 50 frames per second. And the motor that I want is just motor 3. So I'll remove motor 1, remove motor 2, and engage motor 3. And instead of having it run from this position, what if I want Creo to start its analysis with the part at a particular position? So that's a fancy way of saying how can I define the initial conditions of my analysis. And in Creo, you could use this option, the initial configuration, to define that. Right now, your analysis will start from the current position of your movable part. And at the end of that analysis, your movable part most likely would be at a different position. If you were to run the analysis again, then the starting point would be different because now it would start from where the first analysis left it. But if you want your analysis to start from the same point every time, then you have to prescribe the initial condition. And in Creo, we prescribe initial conditions through what are known as snapshots. So grab your piston using the drag component and bring it to the center wherever you want it to start your analysis. And then over here, take a snapshot. I'll call it piston start, and I'll take a snapshot. Your snapshot has been saved. I was hoping that it would be named what I wanted it to be named. Oh, I guess you can't rename it like that. Like, I'm sure there's a way to rename things. Play around with those, with that, and see if you discover something. I'll try to find that as well, but not the biggest of deals. So now if I go to my analysis definition that I was working on, again, this has to be kinematic analysis. And the starting position, I want it to be snapshot, one of the snapshots. In this case, both are identical. I'll select snapshot 1. And when I press run, my linear actuator is actuated for 5 seconds. Let's increase the time to 10 seconds using according to a sinusoidal function that I defined of velocity. I wanted to run for longer or perform more movement. So I'll redefine my motor from here, and I'll modify its profile detail to increase its amplitude to 0.7 and increase its time period to 4 seconds. Yeah, let's see what that does. So one thing that you might have noticed is that it started the analysis from the same position because we had told it that's your starting position. Similar to previous analysis, you can define a measure. I'll define a new measure. I'll select a point on the piston. Struggling. Okay, let's select the. That's not what I wanted. Let's select a point on the connecting rod. Select a point over here, and I want to monitor its position as a function of time. Click OK. I'll run analysis 2. Analysis 2 doesn't provide any data to the first 2 measures. They remain at the same position. It does provide data, but there is no movement happening. But my piston does reciprocate as evidenced by this oscillating position data. So that's the start of our discussion on kinematic analysis and how you can actuate different parts in Creo. I hope the video made sense, and we'll continue our discussion in future videos. Thank you for watching.